So let's talk about a couple things about the residuals. First of all, their expected value is 0. And if an intercept term is included, the sum of the residuals is 0. So that means they can't possibly be independent, right? Because if you know n minus 1 of them, then you know the nth, right? Because they all have to add up to 0. And in fact, as we proceed in linear models, if you fit p terms in your regression equation, then if you know p n minus p of the residuals, then you know the remaining p residuals. And that's because this latter fact that if a variable x is included in the model, then the sum of the residuals times x is also equal to 0. And of course, this statement right here is equivalent to this statement in the case when x is 1, which is the residual case. Okay. So residuals are useful for a lot of things. They're good at investigating poor model fit. They factor into, or they're exactly yield our variance estimate. And so residuals are kind of very important things. So positive residuals are above the line, negative residuals are below. And one way we can think of residuals is they're sort of the outcome y. I'm going through this statement right here. The residuals are the outcome y with the linear association of the predictor x removed. So you might think of it as y adjusted for x is the phrase that's often used. But what it means is adjusted for the linear association with the predictor x, right? If there's a nonlinear association, we haven't gotten rid of that. Often when we talk about regression models, what we're differentiating between is residual variation, which is variation that's left after removing the predictor, from systematic variation, which is the variation that's sort of explained by the regression model. So if there's perfect relationship between the y's and the x's, then there is no residual variation. If beta 1 is 0, if it's just a horizontal line, and only the intercept, then there's all residual variation and no regression relationship. And residual plots can highlight this latter fact. Residual plots can sort of focus in on aspects of poor model fit in a way that the scatter plot can't. And then when you go to higher dimensions with more variables, then you don't even have the equivalent version of a scatter plot. Okay. So let's, create our residuals for our data set that we've been working with. So we're going to do data diamond. This is the diamond data set where we have carats were the predictor and diamond price and Singapore dollars were the outcome. So here I've just defined my y and my x because I don't want to have to keep typing data diamond, or I don't have to type in the data set when I fit LM. So my fit is just LMY tilde x. And you can grab your residuals by just doing resid of that variable that you assign the output of LM to. And you can get your predicted responses at your fitted x's by just using the predict function. And then just to show you that your residuals are exactly the difference between your observed and fitted values, let me just take here my residuals and subtract off the difference between the observed and the fitted values, and then I'll take the absolute value of those and look at the largest difference between my residuals, and you see that it's 10 to the minus 13. It's only at numerical precision, so suggesting that those are exactly the same. And then in fact, let's calculate it here directly, where we, instead of getting the y hats from the predict function, let's put it in directly, where we take the first coefficient, this is beta naught hat, and the second coefficient, which is beta 1 hat, right? I guess R likes to count from 1, whereas, I don't know, computer scientists tend to like to count from 0, so 1 versus 2 as opposed to 0 versus 1, and then multiplied times x, my x value is right here, so this right there is going to give me my yi hats, okay, and then gives you the same exact number when you take the difference between those and the residuals that R puts out. So we know exactly where those numbers are coming from. We can calculate them directly. So here's the residuals. The residuals are the signed length of the red lines in this plot. So we could it's not rotating this plot. It's sort of rotating plot in a way that the vertical distances are preserved, and we could plot the residuals versus x. And that's actually a very good thing to do. Here's the plot, mass in carats versus the residuals. And that's a good thing to do because the reason is, especially when there's a good fit, there's all this kind of blank space right there and right there to hide things. So what sorts of things do you want to look for in your residual plot? You want to look for any pattern. Any evidence of a pattern means that there's some sort of systematic thing that you've omitted in the model that you maybe should have. So here's an example where I'm going to simulate some data and show you a residual plot. So here I generated my x's are just a bunch of random uniform numbers between -3 and +3, and y is it is this line. It's the y equal x line, but then it also has this other part with sine x. Okay, so it's not just y equal x. It's not, and then I add some normal error. Okay, and here's my scatter plot, and here's my fitted regression line, and you can see, in this plot you can sort of see what's going on. You can kind of tell that there's some sort of relationship there that we're missing, that sine x part. But look at what happens when you do it on the residual plot. And you can see it. You can see it much more clearly, right? You can see it exactly right there. Okay, so that sort of pattern in your residual plot would certainly be something that screamed out at you. This something systematic like that. I tried to create an example where you couldn't see anything from the residual plot, but it was, or from the scatter plot, but it was obvious and apparent. And so what I was going to talk about here is heteroscedasticity, and this is a case where our model is not right because the variance isn't constant as a function of x. So here I generated my x's as random uniforms, my y's were x's, so my linear regression relationship holds with an identity slope and zero intercept. But notice here my standard deviation of my normal is, let me just get it. My standard deviation of my normal actually depends on x, right? So that's called heteroscedasticity. So we have, one of the assumptions of our model is that sigma was constant. So again, let's plot it. And so if you plot it, here, look, it looks like a perfect regression model fit with nothing wrong. But if you do the residual fit, you can see the heteroscedasticity very clearly. So you don't often, that's the variance of the response increasing. See the variance increasing for a given value of x. And you don't kind of encounter data like that very often, but it goes to show you the point that residual plots can highlight patterns that are often missed when you do a scatter plot. Plus, not to mention when you go up to higher number of variables, you can't do a scatter plot. You have too many variables. Okay, so there's just two